Hello, dear colleagues. I am happy that you are present at the Moscow State University. Unfortunately, I could not get there today. The talk is devoted to the 85th anniversary of Malyshev, Vadim Alexandrovich. I have known Vadim Alexandrovich for many years because he finished the Moscow State University 1 year later than I am, although I am younger than he, also 1 year. Uh, Vadim Alexandrovich was a very prominent person, and uh, he had many scientific results which are worldwide known, and he has many pupils who are also got the interesting results and are known. Some of them are working at our department. So the life is going on. Thanks to organizer for invitation to talk at this interesting conference. This is the brief outline of presentation. At first, I wanted to list all the directions of modern risk theory. However, I decided that it is too huge task, so I am going to present 4 models, new risk models, in which I made, in which I obtained results. So recall the following well-known facts. To study a real-life process or a system, it is useful to construct a mathematical model. There are a lot of models describing more or less precisely a given system. The same model can describe the processes arising in different research fields. The crucial question in all the investigations pertaining to decision making is how to choose an appropriate mathematical models. Here are the steps which can be presented more clear in this picture. We formulate the real problem, make assumptions, formulate the mathematical problem, solve the mathematical problem, interpret solution, and validate the model. If all is okay, we use model to explain, predict, design, etc. However, if the solution does not reflect the real problem, we have to return to the second step and make the procedure once more. If one is returns to the second step, that explains why one can get a lot of models for the same event, which describe more or less precisely this system. There are always a trade-off between simplicity and precision. A simple model gives the possibility of easily obtaining an explicit solution. However, the poor model fit is the first source of decision errors. A complicated model, giving precise description may also lead to errors, namely numerical solution needed for complicated models and parameters variability constitute the second source of decision errors. And perturbations of the underlying processes provide the third source of decision errors. Thus, the model stability to small fluctuations of model parameters and distributions of basic process is a must. To establish the stability of optimal control to small fluctuation of system parameters, we use the local and global methods of sensitivity analysis, such as Sobel's decomposition, fast or Monte Carlo filtering. For evaluation of underlying process perturbations, we employ various probability metrics. For example, Kolmogorov uniform metric and Kantorovich-Wasserstein one. Here is the general description of input-output models, which are mainly used in applied probability. Here we see the input process, output process, that here is the functional describing the performance mode or the structure of the system. And U, the control, can be applied to the structure of the model. For example, one can use many servers or one server system, or we can use reinsurance in insurance systems, and so on. So T is planning horizon, Z input process, which is given for T belonging to the planning horizon, out process, control process. As I have told, T represents the system configuration and operation model, and the system state is obtained as follows. L sub T of U is objective function or target valuation criterion risk measure, evaluating the system performance quality. It depends on all parameters. However, usually we mention only the planning horizon and control. There exists such model classifications: discrete or continuous time, deterministic, stochastic, or mixed. Mixed means one of the process input or output is deterministic and the other one is stochastic. For example, the classical Kramer-Lundberg model, where premium input is deterministic. However, the demands for identification of clients is stochastic. So we can also consider configuration, dimensions of underlying process, known or unknown parameters and distribution, set of feasible controls. Thus, we obtain static or dynamic models. If we apply the control only once, for example, choosing the initial state or initial capital of the company. And the last point is objective function type. It is interesting to see how the input and output are changed if we change the field under consideration. For example, for inventory theory, the input is supply, output is demand, and the state of systems inventory level. In insurance, we consider premium as input, indemnity as output, and reserve the state of system. In population growth, birth and immigration is input, whereas output is death or immigration, and the state is population size. From the beginning, there was no objective function when studying or dams. On the contrary, reliability approach, minimization of ruin probability, or maximization of uninterrupted work was specific for insurance and reliability. And cost approach, that is maximization of costs entailed by control or maximization of profit, were known in inventory or finance from the beginning. Nowadays, all the applied probability research fields use some or other objective function. A control is called optimal if it provides the extremum of the objective function. It can be infimum or supremum. It depends, for example, as I have told, whether we choose the cost, then we have to minimize, or the profit, then we want to maximize. Furthermore, you start is called an optimal policy. To deal with incomplete information, we need more definitions. Thus, we call a policy stationary if the following relation holds. And an interesting notion is asymptotical optimality. That means that we have this same limit of, for example, cost divided by the length of horizon, the same as for the optimal policy. And a policy is empirical if it's based on previous observations of the system. So the following algorithm is proposed. At first, we suppose all distribution to be known and form the optimal control for any planning horizon. The next step is to find an asymptotically optimal policy, and the last step is to estimate unknown parameters in distribution on the base of previous systems observation and use them instead of exact ones. We prove that such a procedure leads to construction of asymptotically optimal policy. So, in brief, three-step algorithm for empirical asymptotically optimal policy. Key word in all definition of actuarial sciences is risk. Risk is present whenever the outcome is uncertain, whether favorable or unfavorable. Methods for transmitting or distributing risk were practiced by Chinese and Babylonian traders as long ago as the third and second millennia before Christ, respectively. So, insurance is the oldest application in risk theory. However, actuarial science emerged significantly later in the 17th century. See, for example, the interesting book by Bernstein, Against the Gods. The actuarial science has an interesting history consisting of 4 periods: deterministic, stochastic, financial, and modern enterprise risk management. Not only insurance, but other applied probability research domains such as inventory and dams, finance, human theory, reliability, communications, and so on can be considered as special cases of decision making under uncertainty or risk management, aimed at the system performance optimization, thus eliminating or minimizing risk. As I have told, for correct decision making, one needs an appropriate mathematical models. Constructing an insurance company model, one has to take into account its twofold nature. Originally, all insurance societies were designed for risk sharing. Hence, the primary task is policyholder indemnification. The secondary but very important task is dividend payment to shareholders. Discrete time models became popular during the last decade, not only because one can be used for approximation of the corresponding continuous time ones. In many practical situations, discrete time models describe more precisely the real system function. For example, reinsurance treaties are concluded at the end of the financial year. So I begin by considering the first model, ruin probability under a quota share treaty. Let U and VN be surplus or capital of insurer and reinsurer, respectively, at time N or the nth period. U and V are the capital, initial capital, and alpha is the reinsurance quota. Then we have the following equations, where X sub I is the claim amount and Y sub I is the premium amount paid by insured in the ith period. Both sequences consist of IID non-negative random variables and they are independent. We say that the reinsurance at period N if the surplus at period N falls to 0 or below. Hence, the finite time ruin probability with insurers in initial surplus U is as follows. Similarly, for reinsurer. It is possible to define the finite time ruin probability of ceding and the reinsurers in the following way. It is interesting that for the most part, the researcher treated only ruin probability of one side of the common, thus the ruin of insurer, of ruin of reinsurer. However, for example, Dimitrov and others consider the joint reinsurance. Here I present the main theorem giving upper and lower bounds for ruin probabilities. Under the following conditions, we have the ruin bounds where R0 equal to alpha hat R alpha and 1 minus alpha L tilde R alpha is the unique solution of the following equation, which is specific to the case when we obtain the Kramer-Lundberg estimates. The constants are given as follows, and
Ekaterina Vladimirovna, sorry, may I interrupt you?
that
We have a question. What is, in the first line, what is the supremum of x1?
that means that x1 is finite, can take infinite values.
Is it means that x1 is bounded with probability 1, or we have such question? X1 is it's
x1 of omega. For all omega, it is less than infinite.
Sorry, is it support of x1 or it is supremum of x1?
Supremum?
So, did you mean support? Okay.
Yes,
So,
no, not support. It's supremum.
Supremum, of course.
So I don't know. The random variables did not take with positive probability infinite values.
But does it mean that it is bounded by some non-random constant or not?
No, there is no constant.
Oh, no, okay. So in that case, okay, yes, I see.
Not bounded, but can take infinite values. And moreover, the following relation between the expectation, which is called net profit condition. However, not for all omega, x is greater, y is greater than x. So we get the following relation. Is all clear, or are there any questions? Then I proceed. You are welcome to ask questions. The bounds for these probabilities can obtain by two methods, by martingale method and by recursive method. And by recursive method, we obtain the following relations for between probability of n1 plus 1 ruin and n periods ruin in the following way. And as the corollary of the theorem under the same condition, we can obtain the bounds from below and upper bound for joint probability. And there is example when we assume that both sequences are exponentially distributed, and we get that gamma is strictly less than 1. That means the bound obtained by recursive method are better than martingale ones given gamma equal 1. The next model is discrete dual model. We suppose that capital has the following form, where U is the initial capital, M is the firm payment up to the nth period. That means payment 1 per period. The total gain X n up to time n is given by the sum of independent, identically distributed, integer valued, non-negative random variables with finite mean. I skip the history for continuous time dual models due to lack of time. I only mention that such a model can describe a life insurance company dealing with annuities, see example Kramer, or pharmaceutical, oil, telecommunication, venture companies, having a constant expense flow and random gains X sub n. We also denote the ruin probability as follows, and the finite time ruin probability is given by the following relation. In the same way, we define the ultimate ruin probability as the limit of this probability as t tends to infinity. It is possible to obtain the explicit form of ruin probability. We use the fact that equation P of z minus z equals 0 has a unique solution ZF on the interval 0, 1. 1 is not included. Moreover, the ruin probability is a function of initial capital U is given by the following expression. It is interesting to study the order or the behavior of ruling probabilities as we establish some order between two sequences Y and Z. We consider the stochastic order, the well-known definition is the following, and if Y less than Z in stochastic order, then the reverse inequalities are valid for roots and for the probabilities of ruling. Here is the picture illustrating the situation. Next is convex order, defined as follows. The inequality holds for all convex functions f of x for which dimension expectation exists. Then we have the following relation for ruling probabilities. Stop loss order gives the following results. I would like to mention that if we have stop loss order and the expectation are equal, then we get the convex order. Two more orders. Left tail order defined as follows. We have to demand additionally that P0 is less or equal Q0. That is value of probability of zero values for random variables. And moreover, the random variables take only finite number of values. Then for any U positive, we have the following relation. If the condition about the zero value, probability of zero value doesn't hold, then the statement is not correct, and here is given the example. And in the same way, we define right tail order, and the theorem demands that expectation plus zero value for one system is greater than for other. I skip the case when there exists the cooperation between two companies, and only mention that next steps of investigation is consideration of Parisian rule instead of the usual one, thus increasing the system's solvability, then dividends, investments, taxes, and bank loans. And now I show what is valid for bank loans and non-proportional reinsurance.
Ekaterina Vladimirovna, sorry, 3 minutes. Есть.
Да,
3 минуты осталось. Осталось 3 минуты.
да, я знаю.
Ага.
Спасибо. Что успею, то расскажу. Значит, the supposed claims arising to insurance company are described by a sequence of IAD non-negative random variables. XI is the claim during the ICE period, and we use non-proportional reinsurance treaty with retention level A and bank loans. Here is the form of premium required by direct insurer, so we can get the minimal expected additional cost due to bank loan, and using the dynamic programmer, we get the following recurrent relation. The main optimization result is as follows. Under this condition, there exists an increasing sequence of critical levels such that Fn has the following form. The sequence is bounded by Y bar satisfying the following relation. So it is interesting to mention the corollary. For M positive, such statement is not valid. To verify this fact, the numerical analysis was carried out using we establish the model stability using the Ekaterina matrix. The one-step model and the main theorem for n-step model. That's the Ekaterina distance. We also prove the limit theorems, strong law of large numbers, and central limit theorem for surplus. In the same way, we can treat the case of proportional reinsurance. And the last model which I wanted to consider is the model with investment in non-risky model. However, I am not sure that I have time. It's interesting to see that they have the following recurrent relation. So we can obtain the explicit form of Sn and algorithm for ruin probability calculation. And there is the corollary, the calculation of finite time ruin probability. So thank you for your attention.
Thank you. Any questions? Maybe any questions in Zoom? No. Давайте еще раз поблагодарим.
Thank you.
No. We have a question. Sorry. 1 minute. We have question.
Екатерина Вадимовна, я хочу задать вопрос. Вы показывали, вот у вас было два уравнения. Там альфа фигурирует от u минус n плюс сумма y.
Это в которой в первой модели? Или...
И первая, и вторая. В одном альфа была единица, можно показать второе уравнение. Ну, тут скорее вопрос, комментарий. И еще предыдущий слайд. Это было впереди еще.
Раньше, да.
Там, где был, по-моему, Рюин, то, что у вас называется.
Сейчас.
Ну, мы до него дойдем как раз таким образом. Просто я хотела сказать, что такие уравнения очень много тоже в случае, когда, когда критические... Да, вот можно... Ну, потом вы его еще переписывали дальше, когда вот у вас минус n, уже один параметр снос.
Вот здесь.
Да, и следующий, по-видимому.
Ага, следующее, где с банковскими займами и...
Y единица, то есть критические случаи. Вот когда снос 0, они очень часто тоже используются в случайных графах. И тогда это уравнение, оно хорошо описывается диффузионным уравнением. Вот я хотела вас спросить, какие... что...
Диффузионная аппроксимация. Я просто решила рассматривать только дискретный случай, но для непрерывного случая существует диффузионные аппроксимации. И они дают...
Я имела в виду тоже дискретную, но вот в случайных графах там все дискретное, просто потом аппроксимация. Я просто хотела сказать, что они очень часто возникают такие уравнения тоже в разных областях, и особенно критические случаи.
Да, да.
Спасибо.
Пожалуйста. Просто я не могла объять необъятное.